Okay, hello and welcome back. We are thankfully on a much quicker section than the last two, so things should go by pretty quick today. We only have one thing that's really important to cover, and that's this very special operator called the Laplace operator. Sometimes you'll see it spelled Laplacian. Some people will pronounce that Laplacian. I have a habit of doing that. It's the English getting the best of me. It's named after a Frenchman, so you shouldn't say that. It's named after Pierre Simon Laplace. So definitely pronounce it Laplacian. Yes, sound as French as you can when you pronounce that. All right, so what is the Laplacian? It's a generalization of the second derivative to higher dimensions. So in the sense of curvature. So the second derivative calculates curvature for us, and it's very useful in differential equations for a lot of reasons, curvature being one of them, acceleration being the other. Of course, acceleration is always one-dimensional, but the Laplacian in higher dimensions always calculates curvature, and the reason why we care about curvature is that it determines, if you're traveling in a curved path, and you calculate the curvature of that path, then you can determine the acceleration you need to remain on that path. Let's define it. So the way that the Laplacian gets defined is precisely as the dot product of nabla with itself. If we were to actually go out of our way and calculate the dot product of nabla with itself, what does that give us? Well, it gives us, partial x, partial y, partial z, dot with itself, which is going to give me partial squared partial x squared plus partial squared partial y squared plus partial squared partial z squared. So that's what we want to think about when we talk about the Laplacian. And if I scroll down, we'll see that that's exactly what the book's telling us as well. It's each of the partial squared, and then they're added together. So what does this mean? If we take two vectors and add them together, or dot them together, the Laplacian is actually a scalar operator. Okay, instead of being vector valued like the gradient is, it's scalar valued as an operator. Notice the output is a scalar. All right, and we're going to start with some new notation now. Because it's a scalar, we're going to get rid of the bold sign and the over vector, and we're going to use a delta. Okay, so the gradient or nabla is an upside down delta. The Laplacian is not upside down as a delta. It is a perfectly right-sided up delta. Don't get this confused with other deltas that show up that can mean all sorts of other things, right? So don't confuse this for delta meaning change, right? Because we'll often use delta to mean change in something. In general, if you see a delta in physics, it's going to be the Laplacian, because that's the physicist's favorite thing to use. Like, honestly, we use it everywhere. Not that I'm necessarily a physicist, but we do use it everywhere. So we're going to define the delta to be that. All right, so intuitively, we can think about it a few ways. They mentioned the divergence of the gradient, right? Divergence is going to give me that portion, the nabla dot. The gradient is going to give me that portion, nabla. So the divergence of the gradient, you can imagine if I took a scalar function, I calculate its gradient, that's saying how much does it change in each direction. The divergence of that says how much does the gradient spread. Okay, so you can think of a really, really equal in size hill, right? If I just have a hill that looks exactly like this, it's like a very, very flat hill. Well, I shouldn't say flat hill, but it's not curving in any direction, right? The curvature of a hill like this should be really close to zero, even though it's increasing, and that's what we would recover if we had the divergence of the gradient of that hill. It's the sum of the curvatures in each direction, same sort of idea. All right, so let's compute it on this function. So if we calculate delta f, all I'm doing is partial squared f partial x squared plus partial squared f partial y squared. And I'm going to get 2 plus 2 equals 4. So this should have a constant curvature of 4 everywhere. And if you recall, that's the paraboloid. And yes, we know that paraboloids do, in fact, have constant curvatures everywhere. If we have g here, g is this is a special case of the saddle. We can compute g. Delta g is going to be 2 minus 2 is going to be 0. So for a saddle, we actually have zero curvature everywhere. And so there you can look at those. Some will call G a Pringle chip, right? It kind of looks like a Pringles chip. So G has zero curvature everywhere, and that's because this is curvature in sum, right? Nobody's going to agree that G has zero curvature completely, but if you sum all of the curvature in any region, the sum of that curvature will be zero, versus for the paraboloid, it'll still stay positive. So there's something else called the vector Laplacian here. This times, of course, should be an x. So what we do to calculate the vector Laplacian on a vector field is, I guess it's defined like this. I wouldn't do that. I would define it like this, because the top definition is silly and the bottom definition is great. So definitely vector Laplacian, think about it like this. This is going to be, you're going to calculate 3 Laplacians, or you're going to calculate the standard scalar Laplacian on each element of the vector field, rather than calculating the divergence of the vector field and then calculating the gradient of that, subtracting the curl of the vector field and the curl of that. That's going to be a whole lot of extra work versus just taking the scalar Laplacian of each of the elements of the vector field. So definitely define it like this as the bottom case. And just keep in mind, I would say define it like the bottom case. Proposition is that it's the top case. All right, so we can compute one of these. I'm not going to go through it because you've already seen how to calculate partial derivatives, and you're just going to, in this example, calculate the Laplacian on each piece individually. And you'll find out that, in fact, this one is equal to 0, except for at the origin, where, of course, it's undefined because we would be dividing by 0. All right, so that's all I have. Thanks. See you in class.